One of the things that we're trying to do in our research is to electronically communicate and control biological function. So the idea would be, are there ways in which we connect with biological systems through electronics? And can we do this in a very efficacious manner so that we could take advantage of sort of the Internet of Things and all the speed that we enjoy in our communications? The grand idea is are there ways in which, as I mentioned, can we build devices that could either wearable, implantable? Are there ways to communicate and get molecular information that is indicative of the function of biology wherever it may be, and in very rapid form, get that information, take advantage of that, maybe even take a control action to modulate something like eradicate a pathogen from the GI tract, for example. That's the motivation for doing this. It's a small little device that could be put almost anywhere. It's inert, and it just has some electronics, and it could convey information via Bluetooth. So wherever you might want to put that and get information of molecular information. One of the things that's an issue in the Chesapeake Bay is a prevalence of these dead zones where there's oxygen limitations, and fish, you can have a fish kill, or you can have less seagrasses, for example. So you could put these into the bay, they could float, you could have a drone that would fly over, get information, and you could then map out what the specific issues might be. You could put these onto an agricultural setting where you want to know whether or not the right nutrients are applied.
We have a number of peanut processors around the U.S. and even around the world that generate hundreds of thousands of tons of peanut skins as a waste material every year, especially the peanut butter industry. So we have been working for a number of years to try and come up with some way to utilize that material. These peanut skins are very high in phenolic compounds. That's something that we should probably try to utilize and not throw away. Cocoa is a source of these compounds known as the flavonols, which are essentially polyphenols that have had positive impacts on human health. There's a number of food waste materials that also contain these compounds. Peanut skins is what we focused on. We extracted them, encapsulated the phenolics in maltodextrin, which is a carbohydrate that comes from corn that's similar to sugar, but it's not sweet. But it can encapsulate the polyphenols and mitigate the bitterness of the flavor. We're very careful about applying the material because of the high allergenicity of peanut. So we wanted to be very careful not to use the material, anything that consumers would not associate with peanut. So that's why one of the reasons why we picked chocolate, because of the top 10 popular candy bars in America, 5 of them contain peanuts. We gradually increased the amount that was in the dosed piece until the consumer said to us, something's different. And we could get all the way up to past 2.5% before most of our test subjects said, something's different about this. So when we measured the antioxidant activity using a chemical assay, we found that the amount that the consumers were saying, I see something different, was above that of the bioactivity of dark chocolate itself. So that said to us, here's a way to fortify milk chocolate. Consumers won't notice, but they'll get the effect from these compounds that they would get as if they were eating dark chocolate.
I'm going to talk about my work regarding how to how to convert the wastewater grid to the load for pothole repair. And pothole causes lots of money, lots of like millions dollars damage every year in this country. So I'm thinking if I can find a specific material that can encapsulate grit and then convert it to a patch material, the grit can be stabilized and solidified in this material, and this material can be used to patch the pothole. Our pothole repair material gap can be comparable to the conventional patch material, like the cold patch. For conventional cold patch material, normally the application temperature, the lowest temperature you can do is just around 0 degrees Celsius, okay? So it means you cannot feel the pothole very well. But for our gap material, we tested the gap material below negative 15 degrees Celsius, and it still can be solidified very well.
In the course of an exam and cleaning, of course, we want you to leave more like this, right? Where you have these sort of pristine teeth. The problem with that is if you don't go back to a sort of nicely scheduled tooth cleaning, flossing, we within a matter of hours to days, you go back to the sort of plaque that's built up. That's how quickly it begins. We wanted to use an agent that could help prevent the biofilm to begin with. Okay, not necessarily after the fact, after the tooth already begins to show signs of decay. We wanted to look at cerium, the different salts of cerium, as well as the cerium oxides that can form, and those are nanoparticles. So what we did is we compared their activity in limiting the adherence of a specific bacteria that I mentioned previously, Streptococcus mutans. And we did in vitro experiments. So what we found was not all of them inhibited the biofilm. In fact, none of them did under these conditions except one. So there's a couple of conclusions we reached. The size of the nanoparticle matters in limiting the biofilm adherence of these strep species, specifically Streptococcus mutans, but also the manner in which it's made.